Okay, let's take a romp together through the classification of matter. All right, so as you probably remember from elementary and middle school, um, things can be broken down into elements and compounds. Um, we're also going to talk about pure substances and mixtures. That might be something that you hadn't talked about before, and also heterogeneous and homogeneous mixtures, and that might be a new topic as well. Okay, so, as you probably know, elements are the fundamental building blocks of all matter, right? The smallest possible unit of, of any substance is the atom, right? And currently, this is recently revised. There are currently 118 known elements. We've had just 4 of them added in just about the last year or so. Right? And of those, 94 of those can be found in nature. The remaining are only made synthetically, which means they're made in particle colliders and things like that. And most of the synthetic elements have very, very short lifetimes, on the order of a fraction of a second, sometimes as short as a millionth of a second. The particle colliders smash large nuclei together, and they merge and they form some heavier nucleus, and that stays together for a few milliseconds or something like that, and then suddenly breaks apart. But in those few milliseconds, they're able to measure some properties of the atom, and so they can call that a new element. So really, the first 94 are the ones that we're really interested in. The other synthetic elements are really more the domain of physics rather than chemistry. All right, so we've got a periodic table here. Um, in the table, each of the elements is represented by a symbol, either a 1 or 2 letter symbol, right? A lot of these you already know. Nitrogen, for example, here with the symbol N, iron here, Fe, phosphorus, and copper, right? Some of these make sense, like N for nitrogen and P for phosphorus. Some of them seem a little bit odd, like the Fe for iron and Cu for copper. For most of these in which the letters in the symbol don't seem to match the names, usually that's because the letters are based on an old Latin name for that element. All right. So I would like you to get familiar with the names and symbols of most of these elements. Right? So you should learn the symbols for elements 1 through 57 and 72 through 94. What that means really basically is just all of the elements in the main body of the table except the end of that last row. So not these guys, because these are all synthetic elements for which we really can't do any chemistry anyway, right? And most of the guys down here you can ignore. These are fairly unimportant from a chemical standpoint. I do want you to know on the bottom row, I do want you to know these two, lanthanum and actinium. And the main reason that I want you to know those is because these 2 rows here, this first row, I don't think you can see that very well, but that first row is called the actinides, and this second row here are called the lanthanides. Right? And so it's useful to remember the names of those first 2 elements that give you the names of those 2 groups. Okay? So that's somewhat important. And also among these, there are a couple of elements that actually have some importance, the kind of things you're liable to come across or read about in the newspaper. Thorium is a radioactive element that's found in smoke detectors, so it's fairly common, even though it's way down at the bottom of the table. You can ignore praseodymium. We'll never see that. But these guys here, uranium, neptunium, and plutonium, these are also important in nuclear energy and nuclear weapons and things like that. So these come up fairly frequently. You should be familiar with those. Okay. So knowing the names and the symbols is an example of basic knowledge, right? So this is clearly a lower level cognitive skill if we're talking about Bloom's taxonomy, right? So the best way to learn the names and symbols is with flashcards. So I would recommend you get some flashcards. And just set them up like that and work through those and try to learn the names of all of these except for the ones down here at the end of this bottom row. Everything in this row except for lanthanum. And then in this row you can ignore praseodymium and everything after plutonium. Okay. But the others you should know. I would also say I'd like you to learn them all, but go ahead and focus first on the things you've heard of, right? So if you've heard of copper, obviously that's fairly common, you should know that one. You've heard of nickel, obviously that's fairly common, you should know that one. If you haven't heard of rhenium or rhodium or polonium, right, then I would put those down in the second tier, right? I do want you to learn all of them, but maybe prioritize the ones that you've heard of previously. All right, so here are a couple examples. It's just nice to put these up because usually in the chemistry classroom we've got the wall chart, right? But we never actually get to see the elements themselves. The first one, you probably know that's gold. You've seen that before, although maybe not in that form. This one here, a lot of the metals, most of the metals in the middle of the table called the transition metals, they all look very much alike, so it's kind of hard to tell the difference. They all pretty much look exactly like this, but this particular one is manganese. This is bromine. Bromine is interesting because there are only two elements that are liquids, bromine and mercury. It's kind of hard to tell from this picture. It looks like it's just sort of a weird colored cylinder. But what this is really is this is an ampule, which is kind of like a glass vial. And inside that is the bromine. And you can see down here at the bottom, you can see kind of a pool of liquid in there. And some of it has evaporated. And so you can see some orange gas up at the top, which is the evaporated bromine. And finally, this one down here, fairly common, but you probably haven't seen it in this form before. This is sulfur. And if you're ever watching trains go by, you might notice fairly often you'll see these long tank cars. They're almost always black, right? And they've got like a little hood up at the top, right? These kind of tanker cars are used for a lot of different things, but one of the things they're very commonly used for is transporting sulfur. And sometimes you'll see written down here on the side, you'll see molten sulfur. And if you look at the car, the other thing you'll see a lot of times is you'll see just a bunch of yellow stains over here because these cars are filled from the top. That little lid lifts off and then they pour molten sulfur into the car. And when they do that, a lot of it, or some of it, tends to spill out and you get these big yellow sulfur stains on the top of the car. So next time a train goes by, if you see any of these black tanker cars, take a look. Look for two things. See if you can see the words molten sulfur written on the side of the car, and see if you can see that yellow stain up at the top. All right. So elements can be in a couple different forms. We categorize a sample as an element if all of the atoms in it are of the same type, right? So if all of the atoms are iron, we say that's a sample of iron, and that sample is a pure element. If all of the atoms are tin atoms, we say that's a pure element, and the sample is tin, right? But the atoms can be arranged in different forms. There are a few elements, not very many actually. The noble gases on the far right side, helium, neon, argon, krypton, xenon, radon, typically exist as individual atoms, right? So in each one of these balloons, if you could look at it with a very, very powerful microscope, you just see a bunch of individual helium atoms floating around inside each of those balloons, right? Another way that you might find the elements is in molecules, mostly diatomic molecules, but there are some others, right? So any two or more atoms bonded together is called a molecule. And so chlorine is one that typically exists as pairs of atoms. The chlorine gas exists in these little pairs of two chlorines bonded together. And so because there are two atoms in that molecule, we call this a diatomic element. There are some other arrangements. Diatomic is fairly common, especially in the column in the table that includes chlorine, fluorine, bromine, chlorine, iodine. Those are diatomic. Oxygen, nitrogen, hydrogen, a few others. There are some that are unusual but kind of cool. Phosphorus, for example. Makes these little 4-atom triangles. Right? And so phosphorus in the gas phase exists in these little 4-atom molecular units. Right? So my point with that is that it doesn't matter how the atoms are connected. Right? It can be something that exists in single atoms, like helium, or metals, like iron. It can be something that exists in small molecules, like chlorine or phosphorus. So it doesn't matter how they're connected. If all of the atoms in that substance are the same type, if all of them are helium atoms, if all of them are iron, if all of them are chlorine, if all of them are phosphorus, then we say that sample represents an element. Right? Okay, so things that are not elements are compounds, right? So compound is a substance composed of two or more elements. Right? And unlike elements, the smallest unit of compound is a molecule, right? And remember, as we just said a few minutes ago, a molecule is two or more atoms connected together. All right, so that would be a molecule. That would also be a molecule, but this one's not a compound, right? All right. So those are examples of molecules. A really important distinguishing property of compounds is that they have invariable composition, right? And what that means is if you have something like let's say, this guy over here, nitrogen dioxide, that's what I was trying to draw here. The composition of any sample of nitrogen dioxide is always going to be exactly the same. It's going to have the exact same amount of nitrogen and the exact same amount of oxygen. Okay, let's look at some examples of that. All right, so here are a bunch of compounds: water, ammonia, carbon monoxide, and carbon dioxide. Right, water, if it's pure, if it doesn't have any junk in it, right, water is always going to be 88.8% oxygen and 11.2% hydrogen. Ammonia is always going to be 82.2% nitrogen, 17.8% hydrogen. Right? And we've got some numbers over here for carbon monoxide and carbon dioxide as well. Okay? Now, the reason that they have this invariable composition, or constant composition, if you want to say that, is because they're defined by the composition of the molecules, right? Water, as you know, everybody knows water, right, is one oxygen atom and two hydrogen atoms. So we write the formula H2O, and since every sample of water is going to have the same ratio of oxygen atoms to hydrogen atoms, right? It's always going to have twice as many hydrogen atoms as oxygen atoms. Take that 2-to-1 ratio, and then if you include in that also the relative weights of the hydrogen and the oxygen is 16 times heavier than the oxygen. You'll see that with this ratio here, you're always going to get 88.8% oxygen and 11.2% hydrogen. We'll be doing those calculations in a week or so, a couple weeks maybe, so you'll see how that works out. Same thing's true for ammonia. Ammonia is NH3, so that's 1 nitrogen and 3 hydrogens, right? And if you've got this ratio of nitrogen atoms and hydrogen atoms, and you take into account the relative weights of those different atoms, you're always going to get 82% nitrogen and 18% hydrogen. Then we've got carbon monoxide and carbon dioxide. Notice that these are both compounds containing carbon and oxygen, but these are two different compounds because this one has a 1-to-1 ratio and this one has a 1-to-2 ratio. Okay, so these are two different compounds, although they include the same elements. And because they're different compounds, notice also that they have different compositions. Right? Okay. So next I want to look at the difference between pure substances and mixtures. Okay? So a pure substance is any substance in which all of the ultimate particles are identical, right? Doesn't matter whether we're talking about atoms or molecules. If you have something like helium, then the ultimate particles are atoms. If you have something like chlorine, oops, let's do it this way. If you have something like chlorine, then the ultimate particles are molecules. If you have something like water, and again, the ultimate particles are molecules. Okay, so to determine if something is a pure substance, what we need to look at are these ultimate particles. And if all of the ultimate particles are the same, then the substance is a pure substance. Okay, and it can be, a pure substance can be either an element, like here with helium, or here with chlorine, or a pure substance can be compound. Doesn't matter. It can be either, as long as the ultimate particles are the same. Okay. So here's an example. Copper. Copper is an element, right? In order to determine if it is a pure substance, we have to think about what it looks like on the microscopic level, and think about the, like we were saying in the first video, the microscopic representation is what's really important here. Base these judgments on those microscopic representations. And so what copper looks like is this, just a whole bunch of copper atoms in close proximity to each other, packed up together into a nice tight solid. In this case, the ultimate particle is a single atom, and all of the atoms are the same. Therefore, this is an element, and it's a pure substance. Water, on the other hand, is a compound, but if we look at this on the microscopic level, it would look like this. Now we've got two different elements in there. We've got both hydrogen and oxygen, but if we look at the ultimate particles, here, all of those smallest possible particles, all of those ultimate particles are identical. Therefore, this is a pure substance. So, a mixture is a sample in which there's more than one type of ultimate particle. Again, this can be atoms or molecules. If we've got two different kinds of ultimate particles, then it is a mixture. And mixtures can include elements or compounds or both. And unlike compounds, mixtures can have a variable composition. And this is really kind of important. We looked at the slide a little bit ago and showed why water, for example, water is always going to be 88.8% oxygen and 11.2% hydrogen, because the nature of water is defined by this ratio of atoms in that molecule. A mixture is something like tea, right? Tea is water, and then there's a whole bunch of other stuff in there, whatever gets extracted from the tea leaves. So it's going to have a whole bunch of different compounds in it. You might put some sugar in it, you might not. You might put cream in it, you might not. But it's still tea, right? And you can also have strong tea or weak tea. If you're making hot tea, for example, if you leave the tea bag in there for 30 seconds, you're going to get rather weak tea. If you leave the tea bag in longer, for a minute or two, then you're going to get stronger tea, right? In both cases, it's still tea, but the composition of the tea is different depending on how long you leave that tea bag in. Okay, so I got some junk hanging out at the bottom of this. It wasn't supposed to be there. Okay, so let's look at a couple examples of mixtures. Brass. Brass is made of copper and zinc. Right? So this is what brass would look like on the microscopic level. And you can see the ultimate particles here are atoms, and we've got two different kinds of atoms. Right? We've got these zinc atoms and we've got these copper atoms. Right? So this would be a mixture. And seawater, right? Oh, and let me back up a little bit too on brass. You know, we talked about the fact that mixtures can have variable composition. You can have a lot of different kinds of brass, and if you look it up, probably if you go to the Wikipedia page, you'll see some information on this. But you can have brass that's like 90% copper and 10% zinc, or 80% copper, 20% zinc, 70% copper, 30% zinc, or anything in between, and it's still brass. The properties are going to change depending on the relative amounts of copper and zinc, but you can mix those in any proportion that you want, and it's still brass, right? So you can have a variable composition. All right, salt water, right? Salt water is very uniform, but if you look at it on the microscopic level, you'll see you've got a couple different kinds of ultimate particles. You've got these water molecules in there, and then you've also got salts dissolved in there, so you'll have like sodium ions and chloride ions, right? So a bunch of different kinds of ultimate particles in there, therefore seawater is a mixture. Right? And as before, the composition is variable, right? Seawater across the globe is fairly constant. It's about the same, but there are some places like the Dead Sea, of course, where it's a little bit saltier, the density is higher. if you're in the ocean near where where a river empties into the ocean, that's going to dump a lot of fresh water into it, and so the salt concentration is going to be a little bit lower in those areas. Right. All right, and air is also a mixture. Air is a mixture of nitrogen, which is diatomic, and oxygen, which is also diatomic. It's about an 80-20 mixture of nitrogen and oxygen. There are a few other things in there, CO2 and water vapor and a bunch of other trace gases, but it's mostly nitrogen and oxygen. Again, since it's got two different kinds of ultimate particles in there, that's a mixture. Okay. All right. The other thing about this slide, the reason I chose these is to make the point that a mixture can be a solid, liquid, or gas, right? Any of those are amenable to formation of mixtures. All right, so I want to look at an interesting example. This is a little bit counterintuitive, and I don't think I would give you a problem like this on a quiz or an exam, but I want to make the point with this one. In determining whether something is an element or a compound, we have to look at the individual atoms, right? Regardless of how they're grouped, we look at the individual atoms. If all the atoms are of the same type, it's an element. If they're atoms of more than one type, then it's a compound. To see if something is a pure substance or a mixture, we look at the ultimate particles. If all of the ultimate particles are the same, then it's a pure substance. If the ultimate particles are different, then it is a mixture. Right? So a lot of the textbooks have something in them where it has a little kind of decision tree and says that all substances can be classified as pure substances or mixtures, and then pure substances can be elements or compounds, right? And that's mostly true, but there can be some exceptions to that. And so I wanted to look at this example here. All right. Oxygen, under most conditions, is diatomic. So the oxygen that's around us that we're breathing right now is composed of pairs of oxygen atoms linked together. And of course, the chemical symbol for that is O2, right? We just call that oxygen, but to make the distinction here, we can call that normal oxygen. So if we have a sample of oxygen that looks like this, right, we would say that because all of the atoms are the same, this is an element, oxygen in this case, and because all of the ultimate particles are the same, it would be a pure substance. Right? Now, oxygen also can form a molecule called ozone, in which there are 3 oxygen atoms bonded together. This, of course, is really important in the upper atmosphere, where we have the ozone layer that helps screen out ultraviolet rays. So if we had a sample of ozone, like the one shown here, again, we would look at all of the atoms and say, because all of the atoms are oxygen, it is an element, and the element is oxygen, of course. And because all of the ultimate particles are the same, we would say that it is a pure substance. Right? So, again, pure substance, oxygen. This one's O3, and this one's O2. Right? But what if we had a sample like this that contained both O2 and O3? How would we classify that? So, first question, is it an element or a compound? Right? Well, since everything in there are oxygen atoms, we would say, we'd say that it is an element, right? But because we've got 2 different kinds of ultimate particles, it's a mixture, right? So in this case, we have something that is a single element. It's just oxygen. but it's not a pure substance. It's a mixture, right? Because we've got two different kinds of ultimate particles. Okay. All right. Now that's kind of tricky. Like I said, I probably wouldn't put a question like that on a test or a quiz, but I wanted to make the distinction about how to determine if something is an element and how to determine if something is a pure substance. And also to make the point that it's not always true that elements always have to be pure substances. You can, in some circumstances, have a mixture that's still just one element. All right, so here's a couple review questions. For these schematics, the red and blue atoms represent atoms of two different elements. Doesn't really matter what they are. You can think of them as nitrogen and oxygen, or chlorine and bromine, or hydrogen and nitrogen, whatever you want. Take a minute, look through each of these different drawings and determine if what you're looking at is a mixture or a pure substance, and whether it is a compound or an element or both. Okay. Go ahead and hit the pause and work through all of those and write down your answers, and then we'll look at them together. All right, so in this first one, first thing I would do is look at the ultimate particles, right? Obviously that ultimate particle is different than that ultimate particle, so this is a mixture, right? And then if we look at the particles themselves, right, all of these monatomic particles contain only one element, the red one, and all of these blue ultimate particles contain only one element, which is the blue one. So all of the substances in there are elements. So this is a mixture of two elements. All right. Now, in the second one, if we look at the ultimate particles, all of the ultimate particles are identical, right? So that means that this is a pure substance. Right. And if we look at each of the particles all contain more than one element. So it's a pure substance, and that substance is a compound. Okay. That's almost the same as the next one. In the next one, all of the particles are the same, so this is a pure substance. Okay. And each of the particles contains only one element, right? So this sample is a pure substance, and it's an element. Okay, and the last one, if we look at the ultimate particles, we can see there are two different kinds of ultimate particles. There's the one that's only red and the one that's red and blue. So since we have two different kinds of ultimate particles, this is a mixture, and the mixture contains both an element, right, those diatomic red molecules, and a compound, the one that has red and blue, right? So this is a mixture of an element and a compound. All right, there's some problems like that in the study guide. All right, just one last thing to go over in this one, and that is types of mixtures. Mixtures can be subdivided into homogeneous mixtures, which have a uniform consistency, or heterogeneous mixtures, which are non-uniform. When I think about these, to me, the easiest way to distinguish between the two, or to make clear what the difference is between them, is to compare a brownie and a chocolate chip cookie. Right? Both of them have sugar and flour and eggs and chocolate. They've got all the same stuff in there. But the brownie, when you take that brownie, no matter where you bite into it, it's going to be exactly the same here and here and here and here. Right? But chocolate chip cookie has chocolate chips randomly distributed, right? And so if we were to take a sample of the cookie here and a sample of the cookie here, the composition would be different in one spot and another spot, right? So this is homogeneous, meaning same type, right, throughout. And this one is heterogeneous. Okay. Solutions, things like tea. We were talking about tea before, right? Tea would be an example of a homogeneous mixture, because once you put your sugar in there and stir everything up, you got the same consistency throughout. All right, so what we talked about here is talked about the ultimate particles of a substance, and those ultimate particles can either be atoms in something like iron or helium or neon or something like that, or they can be molecules in the case of something like oxygen, which is O2 or O3, or chlorine, which is Cl2, or carbon monoxide, which is a carbon and an oxygen. So those smallest units we're calling ultimate particles in this section. That phrase comes up a lot. And they can be either atoms or molecules. And if the ultimate particles contain atoms of only one type, then it's an element. If there are more than one type, then it's a compound. Okay. If all of the ultimate particles are the same, regardless of whether it's an element or compound, if all of the ultimate particles are the same, then it's a pure substance. If there are different types of ultimate particles, then it is a mixture. And mixtures can either be homogeneous or heterogeneous, depending on whether the composition is uniform throughout or whether the composition varies from place to place within the substance. All right, great. That is elements, compounds, and mixtures. Thank you for your wonderful attention, and we'll be back with another video in a little while.